Hello everyone. Myself, Dr. Ranjith Kumar Gatla. I am working as an associate professor in the Department of Electrical and Electronic Engineering, Institute of Aeronautical Engineering. In today's class, we are going to discuss about single phase full wave midpoint converter, and also we will discuss the effect of freewheeling diode on the single phase full wave midpoint converter as well as the half wave controlled rectifier. These are the topics that we are going to discuss in today's class. So in this single phase full wave midpoint converter, we are going to discuss with two different types of loads. The first one is with R load, and later we will discuss the same single phase full wave midpoint converter with RL load. So this is the basic schematic diagram of the single phase full wave midpoint converter with R load. So here the input that we are supplying to the rectifier is through the midpoint converter, through the midpoint transformer. So as we know, the rectifier input is AC and the output is DC. So here in the load side, we have just considered one R load. And when coming to the configuration, here this the full wave midpoint converter having the two thyristors, namely T1 and T2. Okay, and here when coming to the operation of the midpoint converter, as we know, the input that we are giving is the sine wave. Here let me draw here. Let me consider this is the Vs that we are giving the input. This is the input waveform. And when coming to the output voltage waveform for this particular case, so as we know, here the input AC waveform having the two different cycles. One is the positive cycle and another one is the negative cycle, one full cycle which having. So during the positive cycle, the thyristor T1 will get conduct, and during the negative cycle, the thyristor T2 will get conduct. And here, as we know, here there are three terminals which are namely A, B, and the center terminal of the transformer, which is N. So here, when coming to the supply here, the A is positive with respect to the neutral terminal, so that the thyristor T1 will get conduct. During this time, here the N is positive with respect to the B. Okay, so that's why here the thyristor T2 will not get conduct, only the thyristor T1 will get conduct by giving the gate pulse to the thyristor T1. Because of the forward biased voltage applied across the T1 as well as the gate signal which we are giving to the thyristor, then the thyristor T1 will turn on. So let me consider here we are giving the gate signal at firing angle alpha. So here you can see these are the output waveforms, and I will explain how we will get these output waveforms. So initially this is the input supply that we are giving, that is AC supply. So E is equal to Em sin omega t. Then as we just mentioned, during the positive cycle the T1 will conduct, and during the negative cycle the thyristor T2 will get conduct. So here I have given the firing angle, which is, let me consider alpha, firing angle alpha to the thyristor T1, or after alpha degrees we are giving the triggering pulse to the thyristor T1 or the gate pulse to the thyristor T1. Then the thyristor T1 will get turned on. Then the load current will flow from this point A to thyristor T1 to load to the neutral point. So which means in this case the load current is in this direction. Let me consider this is I0. So the load current is in this direction. And let me consider here the positive voltage, that is plus and minus EDC. In this case, when the thyristor T1 is get conduct. So that's why here after alpha, so here the output voltage will follow the input voltage waveform, that is the sine wave, when the thyristor T1 is conducting. And during this time, because of the R load, so more or less the current waveform also same like as the voltage waveform. So that's why here, so from 0 to alpha, we are not giving the gate pulse to the thyristor T1, even though the forward bias is applied, so that the thyristor T1 is will not conduct. So that's why here during this 0 to alpha, the load current is 0, and when we are giving the triggering pulse, okay, to the gate at alpha, then the load current starts flowing through the load R, then here the current waveform will also follow the same as like the voltage waveform. Then up to this pi degrees. So after pi, the supply will having the negative terminals, which means here the terminals of the across the thyristor T1 will change, and the terminals across the thyristor T2 will also get changed. Then in this case, the reverse biased voltage applied across the thyristor T1, at the same time the forward biased voltage applied across the thyristor T2. So that here the thyristor T2, so that the thyristor T1 will get turned off because of the natural commutation or the line commutation, because the reverse biased voltage applied across the thyristor T1. So because of that, the thyristor T1 will get turned off, and but still in this case the thyristor T2 is also turned off, because at pi we didn't give any gate signal to turn on the thyristor T2, even though the forward biased applied across the thyristor T2. So then after pi plus alpha, here this is pi plus alpha, we are giving the gate pulse to the thyristor T2. Then the thyristor T2 starts conducting, then again here the thyristor T2 will get flow something like this. Follow. And how we are getting in, even though when the during the negative cycle, okay, even though we have applied the negative cycle, then here we are getting the positive voltage, because you can see when the thyristor T2 is turned on, then the load current will flow from here to in this way, which means same like in the first case. In the first case, we have considered the load current flows from in this direction. In this direction is the positive. So in this case also the load current is flowing in the same direction like in the when the thyristor T1 is get conducts, so that the output voltage will also get the same terminals, plus and minus. That's why here in this case when the thyristor T2 conducts, in this case also we will get the positive voltage. Then similarly here the load current also having the same direction like in the first case when the thyristor T1 is conducting, then here the load current again will flow, will follow the same like the voltage. So this is how again after 2 pi, then again the positive cycle, okay, the supply is having the positive cycle, then which means the reverse biased voltage applied across the thyristor T2 and the forward biased voltage applied across the thyristor T1. So because of the reverse biased voltage applied across the thyristor T2, then the thyristor T2 will get turned off at 2 pi, because because of the natural commutation. So then but at 2 pi the thyristor T1 still it will not turn on, because we didn't give the gate signal to the thyristor T1. But after 2 pi plus alpha, we are giving the gate signal to the thyristor T1, so that the thyristor T1 will get turn on again. Then you will get the positive load voltage as well as the positive load current. This is how the output voltage and output current waveforms we will get by operating the thyristor T1 and T2, right? And when coming to the voltage across T1 and T2, okay, as we know, when the thyristor T1 is turned on, then which means it will make it as a short circuit, then the voltage across the thyristor T1 is 0. So that's why here you can see the voltage across the thyristor T1 is 0. Okay, and here during this is in this case the thyristor T1 and T2 both are turned off, right? So that's why we will get the voltage across the thyristor T1 and T2 as something like this, because whatever the voltage we are getting across the thyristor T1, the same voltage we will get across the thyristor T2 also, because both the thyristors are turned off at the same time. Because here you can see in between 0 and alpha, T1 and T2 are turned off in the off state only. So that's why we will get the voltage across the thyristor T1 and T2. Similarly, at pi plus alpha also, the T1 and T2 are turned off. Okay, so that's why here you will get the voltage across this one. Okay, so this is how the voltage across the thyristor T1 and T2 waveform that we can draw, and we can also draw individually. Okay, the voltage across the thyristor T1 and the voltage across the thyristor T2, because in that case you can see here, of course in this case the T1 T2 are turned off, so that we will get let me consider T1 only, the voltage across the thyristor T1. Let me consider, right, it is that, let me consider this is VT1. Okay, so you can see from 0 to alpha, what is that? The thyristor T1 is turned off, so that you will get the same voltage like the supply voltage you will get. But at this case, the T1 is turned on from alpha to pi, so that here the voltage across this one is 0. Then from pi to pi plus alpha, still what is that? At pi degrees, okay, the thyristor T1 is off, okay, which means we will get the voltage across the thyristor T1, which is follows the same. So which means here it will follow up to here. I mean, when it is started to conduct, here no, like this. Then again here when T1 is conducting, then 0. So when the thyristor is conducting, at that particular time, the voltage across the thyristor T1 is 0. Okay, when the thyristor T1 is turned off, at that particular during that time, you will get the voltage across the thyristor, which is same as the supply voltage. This is how we can draw the single phase full wave midpoint converter output. What is that? Load voltage and the load current waveforms, as well as the voltage across the thyristor T1 and T2. Then now the average load voltage and the average load current waveforms that we need to find. So here, yeah, that's what here during the positive off cycle, how the load current will flow, and during the negative off cycle, how the load current will flow, that I have mentioned here. And next, how to find the average load voltage and average load current. Okay, so here we have just now we have discussed how we will get the average, the load voltage and the load current waveforms. So from this load voltage waveform, we can easily find what is the average load voltage. As we know, the standard equation for the to find the average value of any sine waveform, that is let me just write. So V average, which is equal to integral 0 to t into, sorry, before that 1 by t into integral 0 to t Vm sine omega t into d omega t. This is the standard equation to find the average value of an sine wave. So here, but here we don't have a full sine wave, that is the output voltage, because as we know, the output voltage is a DC. Then we have to find the average value for this, the load voltage, that is EDC. So here then we can just, of course here they have just considered EDC instead of VDC. Then EDC, which is equal to 1 by t. So here we need to find the time period. Okay, so what is the time period of this particular waveform? Here the time period, as you can see, if you consider the pi is the time period from 0 to pi, from here to here, the shape of the waveform that you can see, and again from the pi to 2 pi also you are getting the same waveform. So which means here this is the total time period t from here to here. So then when the time period is pi, so 1 by pi integral, here the 0 to t represents the conduction period of that waveform, particular waveform. So here just we have considered here the firing angle as a alpha, and when coming to the conduction period of this waveform is, because from 0 to alpha there is no conduction, and but here it is start conducting from alpha to pi, because the total time period is pi only. Okay, so the maximum what is that duration to conduct that, the maximum limit to conduct here, the t, this t and this t are same. Okay, right, from, but the 0 is here not, it is not conducting from the 0, it is conducting from alpha. So then the limits are from alpha to pi into, here of course instead of Vm, here we have just considered as a Em sine omega t into d omega t. Then if you simplify this, then you will get average load voltage. So here it is very simple. Then 1 by pi into, if you apply, of course here just let me write Em by pi into the sine omega t is nothing but minus cos omega t. Okay, and with the limits of alpha to pi. And if you simplify this, then you will get the EDC, which is equal to Em by pi into 1 plus cos alpha, because here cos pi is what is that 1 and minus cos alpha, so minus of minus plus, so that's why here 1 plus cos alpha that we can get. So this is the average load voltage. Similarly, the average load current, let me consider here ID. ID is equal to, which is EDC by R, because here the load is, we have just considered as a resistance R. Then here ID is equal, the load current ID is equal to, here EDC is just now we have calculated, that is EM by pi into R into 1 plus cos alpha. Right? So this is ID is equal to EM by pi R into 1 plus cos alpha. So this is how we can find the average load voltage and the average load current. The same thing just I have mentioned here also. Here the first thing EDC is equal to 1 by pi into alpha to pi, and then just now we have calculated, and finally we will get EDC is equal to EM by pi into 1 plus cos alpha. Similar way, the average load current also, I mean just EDC by R, then you will get EM by pi R into 1 plus cos alpha. Then how to find what is that, the RMS load voltage. So here the RMS load voltage, as you know, what is that, the standard equation for the RMS load, I mean RMS value of any waveform. Just now we have seen the waveform output voltage and current waveform. So for this here, the VRMS, which is equal to 1 by pi into, again sorry, not pi, I mean the standard equation here, it is 1 by t. So 1 by t into integral 0 to t into Vm sine omega t whole square into d omega t whole to the power of 1 by 2. This is the standard equation to find the RMS value of an sine wave. So here then we have to write the equation for the what is that, the output waveform that we have drawn for the single phase full wave midpoint converter. So anyway here we have just considered as ERMS, instead of V we have considered as ERMS, and here the time period is same again, 1 by pi, and the limits also, the conduction period also just now we have seen not 0, this is alpha to pi, alpha to pi into here we have considered as, instead of Vm here we have considered Em sine omega t is alpha, sine alpha, not alpha actually, sine omega t only, because after limits we will consider it as a alpha omega t whole square into d omega t whole to the power of 1 by 2. Then if you simplify this one, then you will get 1 by pi into here these integral alpha to pi Em square into sine square omega t into d omega t whole to the power of 1 by 2. So here we can just write the sine square omega t as a, so here Em square, let me write Em by root pi, okay, Em by root pi into, here the sine square omega t, that we can write it as a 1 minus cos 2 omega t by 2 into okay, into d omega t whole to the power of 1 by 2. Then apply the integral to this 1 minus cos 2 omega t by 2. So then we will get here Em by, here the 2 also I have just taken taking the common, so Em by root 2 pi, because here I am taking from 1 by 2, so root 2 pi into, here the one I mean the integral of 1 is here the omega t, minus here the cos 2 omega t is sine 2 omega t by 2, and with the limits of alpha to pi and whole to the power of again 1 by 2. Then if you simplify this, then you will get this Em by root 2 pi is what is that common, then here omega t, that you will get pi minus alpha minus what is that, sine 2 alpha, because sine 2 pi which is equal to 0 by 4 pi, okay, whole to the power of 1 by 2. Then finally ERMS, which is equal to EM into pi minus alpha by, sorry, this is 2 pi not 4 pi, okay, pi minus not 2 pi, when this is just 2 alpha by 2 only. So here just I am taking again the 2 pi inside, so that here pi minus alpha by 2 pi here it is, and what is that, minus of minus, here it will get plus, okay, so plus sine 2 alpha by because here again 2 pi 2 to 4, so 4 pi whole to the power of 1 by 2. So this is the RMS value of an load voltage. Then the load current, RMS value of an load current is just similar like the average current. So IRMS is equal to ERMS by R. You can just substitute this ERMS in this equation from the above equation, then you will get the ERMS value. This is how we have to find the load voltage and as well as the load current, what is that, average load voltage and load current, as well as the RMS load voltage and load current equations. So these are very important to solve the numerical problems. So we have to remember these equations, right? Then yeah, the same thing I have mentioned here, because this is, so suppose if you take for firing angle alpha is equal to 0, then what is the ERMS? That ERMS is equal to EM by 2. ERMS is equal to EM by 2, because here this is just you can see EM into here pi minus alpha is equal to 0 by 2 pi, and sine 0 is equal to 0, so 0 by something is 0 whole to the power of what is that, 1 by 2. So here pi gets cancelled, okay, and here 2 pi, then here EM by, how here it is get 2 pi gets cancelled, so EM by root 2 actually, not EM by 2, okay. So this is how we can get this ERMS is equal to EM by root 2. Then same RMS value of the current is equal to ERMS by R. Then next is RL load, okay. So then here more or less what is that, the operation of the single phase full wave midpoint converter with RL load is also same as like the R load, but here you can just see only the difference. Of course here just we have considered the load current as constant, because here the load current is depends on the value of the inductor here. So if you choose more inductance value, then you will get constant load current. So here we have just considered the high value of the inductor, so that here we are getting the constant output DC current. But when coming to our load voltage waveform here, so when compared to R and RL load, here you can see the negative voltage also that we are getting during the other thyristor is turned off, because which means, as we know here, this is the waveform that we have what is that, discussed in case of R load. But here in addition to this, here as we know, during the positive cycle the thyristor T1 is conducting, and during the negative cycle the thyristor T2 is conducting. So anyway, this let me discuss the same option. During the positive cycle here, as you can see, when the thyristor during the positive cycle, the forward biased voltage applied across the thyristor T1, and at the same time, after an angle of alpha, we are giving the gate pulse to the thyristor T1, so that the thyristor T1 will turn it on. Then the load current will flow in this direction, as we have discussed in the previous section. Same like here also, the load current will flow in this direction. So which means the load current direction is in this way. So during this time, the inductor will store energy in this way. Store energy in this way. Okay. Then, of course, then the load voltage that we will get here. same like as your supplied voltage. Okay, but after pi, okay, so you are, even though you are applying a reverse biased voltage, because the energy stored in the inductor will get discharged, okay, by reversing the terminals like plus and minus. Then the some what is that, some load current, I mean the energy will flow through the thyristor T1 in a reverse biased, because here the forward biased is in this direction, but it is going in a opposite direction. So that's why up to thyristor T2 is turned on, here the thyristor T1 will conduct in the reverse biased. Then when the triggering pulse we are giving to the thyristor T2, okay, then immediately the thyristor T1 will get turned off and the thyristor T2 will get turned on. Then again the load voltage we will get in this way. And when the thyristor T2 is conducting, again here, because from during the pi to pi plus alpha the inductor is discharged, and when the thyristor T2 is conducting, again it will charge with these terminals like here, plus and minus. Then when the thyristor T2 is turned off, okay, I mean after 2 pi, still the thyristor T2 will conduct, okay, up to 2 pi plus alpha, because here still it is supplying what is that, the source, I mean the energy is supplying through this inductor, so that the thyristor T2 is still turned on, but in a reverse bias, direction. When you are giving the what is that, the triggering pulse to the thyristor T1 or gate signal to the thyristor T1, then the T2 will immediately turn it off and the T1 will get turned on. So like this cycle will repeat, right? So because of the inductor we are getting some negative voltage in the full converter. And anyway, here the load current that we have just considered as a constant because of the by taking the high inductance value. So here that you can see during positive off cycle, what is that, the load current will flow from point A to thyristor T1 to through the load R and L and through the N. And similarly during the negative off cycle, here the B to thyristor T2 to the R, L and to the up to N. Then in this case, as you can see, the same points I have mentioned here, you can see just during positive off cycle, okay, right, the supply voltage SCR T1 is in the forward biased, but still even though if it is in the forward bias, still the thyristor will not turn on until we give the gate signal at at an firing angle alpha or a triggering angle alpha. The T1 starts conducting, because at that particular point we are giving the gate signal to the thyristor T1. Okay, then here the inductor starts charging with the load current. Okay, and when the supply is reversed during the negative off cycle of the supply, then the inductor changes its polarities and start discharging to the T1. So that's why T1 is in the on state only till that point. Then when the thyristor T2 is triggered at pi plus alpha, then T2 starts conducting. So again the inductor stores the energy. So because of the inductor effect here, the load current may be continuous or maybe it is continuous, but in some cases it may be discontinuous also, but it depends on the value of the inductance. So if you are choosing the high value of the inductance, that's what here just I have mentioned in the green color, large the inductance current is more continuous and less ripples. So that's why in this case just we have considered the inductance value is very large, so that's why we are getting the constant load current. Then in this case also we have to find the average load voltage and the average load current. So here just I have mentioned here how to find. The similar way here also, okay, so based on the output waveform only. So here let me you can just see, let me write the basic equation. As we know the basic equation, again I am writing here V average, which is equal to 1 by T into integral 0 to T Vm sine omega T into d omega T. Then here 1 by T, again here T is the time period. So again here we have to identify what is the time period. Again just let me consider 0 to pi. Okay, so 0 to pi you can see the shape of the waveform, and pi to 2 pi also you can see the shape of the waveform. So what is the waveform that we are getting 0 to pi, the same waveform is repeating from pi to 2 pi also, again 2 pi to 3 pi also. So which means again here the time period is pi. And the limits of conducting this waveform. So again here it is starting from alpha to how long it is conducting? Not pi. Up to pi plus alpha it is conducting. So that's why here from alpha to pi plus alpha. That is the conduction period. Again this is same Vm sine omega t into d omega t. Then if you simplify this, we will get, of course here we are just considering as a EDC, the EDC value. The same thing here I have mentioned, just we can see. The EDC is equal to 1 by pi into integral alpha to pi plus alpha Em sine omega t into d omega t. Similarly, the sine omega t is nothing but minus cos omega t, and you are applying the limits alpha to pi plus alpha. So which means here you will get here, what is that in this case? So 1 by pi into Em into pi plus alpha, already minus is there, minus and minus, what is that, sorry, cos pi plus alpha, right? Okay. Yeah. So here, so which means cos alpha minus cos pi plus alpha, that you can get. So if you simplify this one, then you will get what is the Em by pi into 2 cos alpha. Okay, Em by pi into 2, because already minus is there, so we have just to multiply this one. So that's why here we are getting the minus cos pi plus alpha and plus cos alpha. But here the cos pi plus alpha is nothing but again minus cos alpha. So cos alpha plus cos alpha, here you will get the 2 cos alpha. So 2 Em by pi into cos alpha. This is the average load voltage in case of RL load. But in case of R load, what is that? We got the equation. Just we can see in case of R load. Yeah. So this is RMS voltage value, and yeah, this is Em by pi into 1 plus cos alpha. Em by pi into 1 plus cos alpha. Yeah. So here Em by pi into 1 plus cos alpha. This is in case of R load, and this is in case of RL load. Then similarly we can find the average load current, that is average load voltage by the resistance, so that you will get the average load current, that is 2 Em by pi r into cos alpha. And here also let me consider when alpha is equal to 0, okay, that EDC is maximum, because alpha is equal to 0, cos alpha is equal to cos 0 is equal to 1, so that you will get 2 Em by pi, that is the maximum value when alpha is equal to 0. And when alpha is equal to 90, EDC is equal to 0, because cos 90 is equal to 0, so the EDC value is 0. EDC is 0. This we can also explain with waveforms. Here you can see this is alpha is equal to 30. When you are increasing the alpha value, okay, then the EDC value, when you are increasing the alpha value, the EDC value will get decrease, which means the EDC is inversely proportional to alpha. Why? Because you can see, if you are increasing the alpha value, this negative portion will get increased, so that the average value, the total average value will get decreased. So when alpha is equal to 90, suppose if alpha is equal to 90, then you will get the same, whatever the negative cycle is there, the same amount you will get the positive cycle also. So this positive cycle, negative cycle will get cancelled, then you will get EDC is equal to 0. And when alpha is greater than 90 degrees, okay, then the EDC value is negative, because the negative portion will having more than the positive portion. So the average value will get negative. So this is how here, based on alpha value, the output voltage will get changed. Then this is what the difference between what is that R and R load. Of course, when alpha is equal to 30, more power is fed into the load, because the positive voltage is nothing but the supply is from the source to load. Okay, and as the firing angle is increasing, the average DC output voltage decreases. Just now we have discussed how it is decreasing. and at alpha is equal to 90, the load voltage contain equal positive and negative areas, so that the average output voltage is is 0. And when the firing angle is greater than 90, then the DC voltage goes negative, which means in this case the load is supplying to the source. The load is supplying to the source. The same like the full bridge inverter that we have discussed in the previous class. Okay, in the full bridge inverter we can operate in the two quadrants. Okay, two modes. One is in the rectification mode, another one is in the inversion mode. So the rectification mode is nothing but the source will supply to the load, and the inversion mode is nothing but the load will supply to the source. Okay, so which means from 0 to 90 degrees it will act as a rectifier, and from 90 to 180 degrees it will act as a inverter. The same concept here. And the next thing is the effect of the freewheeling diode. Actually, as we know, the major advantage about the freewheeling diode. Okay, usually the freewheeling diode we usually connect in parallel with the load. Okay, or across the load. So here the freewheeling diode prevents the load voltage becoming negative when the supply voltage reverse, because as just now we have seen in the RL load, okay, because of the inductor value, here the load voltage goes into the negative during 0 to alpha, and as well as during 0 to pi, as well as in between pi and pi plus alpha. To prevent that one, here we are using the the freewheeling diode. Of course, the purpose of the freewheeling diode is different in different circuits, but here in this circuit, here the purpose of the freewheeling diode is to prevent the negative supply voltage. Sorry, the negative load voltage. Okay, so that's why here you can see the same thing. Of course, here during the positive cycle the thyristor T1 will get conduct, and during the negative cycle the thyristor T2 will get conduct. But here when the negative cycle is applied, that time the inductor will get discharged, because during the thyristor T1 is conducting, it will charge like these terminals. Okay, and during the negative, okay, so here it will discharge plus minus. Okay, so it will discharge through this freewheeling diode only. Okay, instead of the thyristor T1, the freewheeling diode only. So that's why here you can see the output voltage waveform. So here from 0 to alpha there is no voltage, and alpha to pi, and again here during the pi to 2 pi, again the inductor will discharge through the freewheeling diode D, and again here from 2 pi to 2 pi plus alpha, and pi to pi plus alpha also it will happen same thing. Okay, so that is the advantage of the freewheeling diode in the full wave midpoint converter. And we can also discuss the same the freewheeling diode effect in half wave rectifier. Okay, and in the half wave rectifier, this freewheeling diode is also called as the commutating diode, or the flywheel diode, or we can also call as bypass diode. Then why we are calling as this one? Because here the freewheeling diode we can also use to get the continuous current mode operation. Because especially in the half wave rectifier control. In the half wave rectifier control, as we can see, if there is no freewheeling diode, so we will get only the load current during the when the thyristor is conducting, because during the negative cycle we will not get any load current. But here, because of the freewheeling diode, okay, so because when the thyristor T1 is conducting, anyway the load voltage that we will get, okay, and at the same time the load current also we will get. But when the thyristor T1 is turned off, then the load voltage is 0. But here, if there is no diode, then the load current will also get 0. But because of the freewheeling diode here you can see during the thyristor T1 is conducting, the inductor will store some energy, and during the thyristor T1 is turned off, then the inductor will discharge through, because here while charging here it is plus and minus, and while discharging here it is minus and plus. So which means the forward bias applied across the freewheeling diode, so that the diode will get conduct, so that still the load will having some current. So that's why here, see, you can see when the thyristor T1 is conducting, the load current gradually increasing, and during the thyristor T1 is turned off, the small current will flow through the load because of the inductor. Then here the load current will gradually decreasing, right? So, and during what is that T1 is turned off, again here it will having some small current. Then after again we are giving the triggering pulses after 2 pi plus alpha. Then again the thyristor T1 is turned on. Then again the load current will gradually increase. So here, as you can see, there are two purposes of this freewheeling diode. The in the midpoint converter, the purpose is different, and here in the half wave rectifier, the purpose is different, right? So as we can see here, the diode mainly the diode having the two functions. Anyway, here this function is same like in the what is that previous case. Okay, so that is, it prevents reversal of load voltage, of course, except some small diode voltage drop is there. Okay, these are the two main functions of the freewheeling diode, and it also transfers the load current away from the main rectifier, so thereby allow all of its thyristor to regain their blocking state. These are the main two functions of the freewheeling diode. This is all about the effect of the freewheeling diode in the two different cases. One is in the midpoint converter, and another one is the half wave rectifier. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.